Are we good to go? Should we go? Okay. Hi everyone, welcome. Thanks for coming by. Not yet. Okay. Before I start, just want to give a quick shout out to Derbycon for giving us the opportunity to present today. You guys are doing a great job. Right, about it. Go ahead first.
So I am Nick Delewski. I'm a managing consultant with Spirent Security Labs. With Security Labs, I'm a pen tester, red teamer, focusing mainly on network type attacks. I do also help out with a little bit of embedded wireless and IoT type projects. I'm also a physics enthusiast, so I apologize in advance if any math or science jokes come out in today's presentation.
I'm Saurabh Harit. Feel free to butcher my name. Goes by the handle 0xSaurabh. I work at Mandiant FireEye, and just like everyone else these days, I'm also a red teamer because it's trending on Twitter. Also a wannabe reverse engineer, and for all the recruiters in the house, I'm also a security researcher, trainer, and speaker. Right, this is what the agenda for the talk looks like. We'll start with an introduction to connected medical devices. We'll talk a little bit about the architecture and workflow of these devices. We'll talk about what are the good aspects of it and what is bad or could be bad. And then we'll touch upon the threat surface from a penetration tester's perspective associated with these medical devices. We'll talk about some of the real-world attacks that has happened against medical devices, and after we have wasted most of the time, then we'll jump into the case studies where we'll talk about the vulnerabilities that we discovered in a couple of medical devices. In a typical InfoSec style presentation, we won't be providing any solution to any of the problems we'll talk about. But there will be some generic closing remarks.
So just a couple of notes about some of the medical devices we're going to be talking about today. They are still deployed somewhat. We are going to be talking about a device that has been improved upon over the last several years with increasing focus on medical device security. However, there are likely still these devices out there in the ecosystem. And therefore, we will have some heavily redacted screenshots. Some details like port numbers and things will be changed. So please expect that.
Oh, this is easy.
So when we're talking about healthcare devices, we're talking about a wide variety of different things. There are, your classical connected healthcare devices, things that you would find in a hospital or a doctor's office, more clinical medical devices. Then you have things that, might be, more aimed toward the consumer market, things that help you improve your lifestyle, Fitbits, health trackers, some apps on certain wearables, that kind of thing. So all of these devices are collecting and processing different data about you. Essentially, it's all data that can, in certain contexts, be construed as medical data. This data is proliferating, sometimes in ways that we wouldn't quite expect. And it's important to take a look at these devices, how they're handling your data, what protocols this data is being transmitted over, and what is done with that data after it's collected and processed.
Right. So we tried to classify medical devices into 5 different categories. And the first one, you'd be most familiar with it, are the consumer variables. So your fitness trackers would be part of it. Then there are patient monitoring devices, which are like insulin pumps, ECG, heartbeat monitors, and so on. And then IVD, or in vitro medical devices, are your HIV detection systems. And then all the devices that I've talked about so far, they are external to a patient's body. But then there are embedded devices which are implanted in patient's body. So like most common example would be your pacemaker. And then finally, there are these huge, bulky, stationary medical equipments that you usually see at the hospitals, like medical dispensing systems, MRI machines, CT scanner, and X-ray machines. This is what a typical data loop for an IoT medical device looks like. So the device is always in constant monitoring mode using a sensor. In case of an event, it triggers an action, and then finally the data is aggregated and analyzed. So if you take a quick example of an insulin pump, it uses a sensor to constantly monitor blood sugar level of a patient. And if the blood sugar level drops, it injects right amount of insulin into patient's body using a catheter, which is usually placed under patient's skin. And then once that action is taken, the data is then gathered and analyzed. And I think that aggregation and analysis part of the data is going to be the most important to watch out from connected medical device perspective. In terms of architecture, the device itself on the further left side has a lot of subsystems. So first of all, they can talk on tons of protocols, so Wi-Fi, Lo-Fi, IRDA, Ethernet, Zigbee, Z-Wave. Then a typical connected medical device would have a sensor and actuator to, say, for example, to monitor your heartbeat or insulin level. And then most of these medical devices are actually heavily monitored and maintained by the device manufacturers themselves. So there's some sort of remote access, which also could be interesting from security perspective. It would have a display, a location tracker, especially if the device is something that tracks your steps. Then there's device association module, which would be responsible for authenticating and authorizing a device onto a network. Storage, it will gather data from the patient and then would have some sort of small storage. Event architecture is another important module because it, based on the data it gathers, it analyzes the data and then creates a trigger. And then there's command and control, which is a hacker's paradise. Then middleware, you can think of middleware as like a web server for your medical devices. So it handles most of the code for authentication, authorization, command and control. But I think the most important part would be the database part, because this is now taking all the data from different medical devices and then processing that data, and then it outputs the consumable data set, which can be just fed into through APIs into the third layer, which is like management interface. So like this kind of data can be used by the patient themselves to monitor their health, by the doctors to monitor a patient's health, like, and take preventive measures by device manufacturers. They can use the data to better the device for future use and so on.
So why would we want to connect our medical devices? I think there's a lot of people out there that would have a lot of good reasons for why we're doing this, why we're doing what we're doing. Some of it is even encouraged, mandated by legislation in various countries, having to do with electronic health records, the efficient sharing of medical data, the availability of medical data in an emergency, making sure that medical data is portable to various providers and not in proprietary formats. So when you're talking about connected medical devices, there's a lot of stuff that makes sense. It enables remote health monitoring, so you can spend less time in the hospital if a doctor can read your implantable device for signs of heart problems from home. You receive better quality care if you have more accurate instrumentation, if you have instrumentation that is, say maybe remotely calibrated, or the data is able to be sent to, an expert in the field at a moment's notice, as opposed to, an overworked general practitioner who has to deal with all different types of patient complaint at once. You can get some faster response time, again, from that instantaneous communication. Also, telehealth, telemedicine is becoming increasingly popular, where you can actually get, in some instances, a full consultation or examination remotely. I've heard instances of hospitals implementing what were affectionately called robot doctors, where you have essentially an iPad connected up to a remote-controlled car, more or less, and these drive around the ward, and the doctor comes in and say, "Hi, I'm your doctor. I'll see you now." Some people are a little bit put off by the concept, but when that doctor is actually one of the preeminent experts in the country or in the world on that particular malady. A lot of people would rather have that expertise than be put off by the fact that there's that remote connectivity there. In addition, you're able to get early warning of things that might be a trending problem. So, for example, with insulin monitors, if your blood sugars are trending downward, you can send an alert not just to yourself, but if, for example, your sugar is already at a low level, or if your reaction to low blood sugar means that you're not able to see that alert, if there's that ability to maybe get that information to another safety contact, that also has the potential to benefit the patient in the long term as well.
All right, and then obviously there are some nightmares that are connected to the growing number of medical devices. So first of all, I think in my opinion, the biggest challenge would be for hospitals and medical institutions to accommodate large and growing number of medical devices. So I think there are already quite a large number of connected medical devices per bed in modern hospitals in the US. And if you factor in other devices like portable medical devices, which patients might start bringing, then that will also cause a lot of chaos. So hospitals, first of all, must make sure that they have enough bandwidth to support all those devices, and then their wireless infrastructure doesn't choke because of the growing number of devices. There's also the issue of network segregation. So how do you distinguish a legit device from a malicious or rogue medical device? So, and also we will talk about some of the malware in next few slides about how they can compromise medical devices and use them to pivot and then launch further attacks on the hospital system. So last thing we would want is that one compromised medical device affecting the other medical devices or other systems on the hospital network. So that's also going to be important and also going to be a huge challenge to segregate these medical devices. We already talked about how like these medical devices support different kind of communication protocols. So especially devices by different manufacturers, it could be a challenge to get them to talk to each other. Authentication and authorization is also going to be an issue because you need to figure out how to authenticate these devices, and also more importantly, how to authorize these devices to different segments of the network and what systems and subsystems they can access. Patching, a lot of devices are which are now connected, never meant to be connected to the network. So they are typically what do you call legacy medical devices. They never had any connectivity subsystems built into them, and then we'll talk about in the next slide how they're connected to to the network. So there's that issue as well. Right. So like I just mentioned that there are some devices which were never meant to be connected to the network, but here we are because they thought we're connecting everything to the network, so why not devices as well? And so how these medical devices are connected to the hospital network are using serial to Ethernet converters, and that's just a terrible idea. So these devices, they connect to the serial communication port. They've never had any security built into them. In fact, Department of Homeland Security last year alerted against one of the most common used serial to Ethernet adapters, which is N-port, developed by a company called Moxa. I hope no one is here from that company. But apparently, like, there were 3 critical vulnerabilities. One was that would allow an attacker to extract sensitive information remotely without authentication. The other one would allow an attacker to upgrade or downgrade firmware, again remotely without authentication. And as if that was not enough, there's also a buffer overflow vulnerability that you can exploit to get remote code execution on these devices. I don't know if you guys remember, like the unscheduled power outage in Ukraine that happened in 2015. So as per DHS, that also happened because someone corrupted a bunch of these adapters remotely.
So when we're talking about any kind of IoT device, I like to think about it still in the same terms as I would a network pen test or an enterprise network pen test. Layers 1 and 2 may be different, but ultimately we're still just connecting together a bunch of network nodes. Now, in any kind of a pen test, you know that open source recon is going to be a key. It can make your job a lot easier. It also gives you a much more realistic picture of, you know, is this particular vulnerability exposed? Are there any other compensating controls that are out there? So one of the things that you can do with IoT devices, you can take a look at the device itself. You can take a look at the interfaces that are on it. You might be able to download data sheets. You might be able to get regulatory data that's been filed about these devices. That's great. That's one kind of open source reconnaissance you can do on it. Another piece of information, though, that will really give you a lot more insight about the actual risk profile is to learn about the life cycle of these devices. How are they deployed? How are they maintained? How are they retired? As we've seen in the news in the last couple of days, supply chain attacks are real, or are they, depending on who you ask. So if you have a device that you know is vulnerable to a physical attack and it's kept under lock and key and it's also tagged with an active RID or RFID tracking unit, you know, that's a device that, you know, has some of the risk mitigated in there. It might open up some additional attacks, namely being able to tie that active RFID beacon to a particular patient. So you're always making a trade-off. Personally, as I mentioned before, I like physics. I think that risk is an awful lot like the physics concept of entropy, which is entropy is always increasing in the universe. I think as long as we are adding more devices to the network, as long as we are expanding the amount of data that's being shared from place to place, risk is also constantly increasing, and we as security professionals, we're just trying to minimize that increase until we actually kind of reach an equilibrium there.
All right. So I'll talk about some of the horror stories. Actually, there are tons of horror stories associated with compromised medical devices or connected medical devices. But I specifically wanted to talk about MedJack and MedJack 2. MedJack, also known as medical device hijack, is a malware that came out in 2015, lived through most of 2016. MedJack 2 is actually a more sophisticated, newer version that came out in 2017. And so MedJack exploited older operating systems like Windows NT, 2000, 2003, XP, all those. Like one of the interesting things about MedJack was that it went undetected for the most part. And the reason why it happened was because it exploited vulnerabilities like MS-08067, which are like old vulnerabilities. So all the modern operating systems have already protection against MS-08067. So the modern operating system would just drop the packet. It won't even reach the endpoint. And the medical devices which are running the older operating system, they didn't have any endpoint installed on them, so it went undetected for the most part. So it compromised tons of medical devices on hospital network and then used those compromised devices to pivot and launch further attack on the hospital network. It was also known to use Citadel and Zeus malware for horizontal privilege escalation. So yeah, it caused a lot of damage at that point of time.
So the first device that we're going to be talking about is an older model of connected IV pump. Now, what I'm going to talk about today are mostly, architectural and design decisions that were made when this pump was being engineered and manufactured. I don't think that the modern focus and the modern capabilities of the red team or attackers were being considered when this device was designed. So as I've mentioned before, successive iterations of IV pumps have gotten progressively more and more secure, and that's in part to the efforts of the FDA to really put a focus on the need for medical device security. It's also, I'd like to give a shout out to organizations like I Am the Cavalry, who put on the Biohacking Village, or involved with the Biohacking Village at DEF CON, really spreading the awareness of medical device security and helping to increase accessibility of these devices to researchers who just want to make things better for everybody. So I think that there's been a lot of improvement going on here, and we're going to talk about some of the things that we find in these legacy devices that really need to be engineered out of current and future solutions. So as I mentioned, the device is an IV infusion pump meant for injecting nutrients and medication to active patients within a clinical setting, mostly. It is used for controlling the dosage of medication that's being administered, and it has a master drug list on it, and that drug list sets limits so that it reduces medication errors. They can be changed depending on the floor of the hospital, the care area of the hospital, because sometimes you might want the emergency department to be able to issue a certain dosage of a medication that would be maybe inappropriate for maybe a less acute setting, such as a normal medical surgical floor. They used to be completely standalone devices that you can program at the bedside. While those devices are still out there, those standalone devices are still out there, I think that more and more settings and more providers are moving toward these connected devices because they integrate well with EHR systems and other hospital systems. Again, these are random images. It was not this pump that we were looking at. So at a high level, you have the infusion pump at the patient's bedside, connects to a wireless access point. In some infusion pumps, it might use a proprietary access point that uses ISM band communications that are dedicated to medical devices. In some instances, it might use the same Wi-Fi frequencies that are available to everybody else. And then through that access point, it'll connect to a gateway, possibly to some cloud services back at the manufacturer for updates or other telemetry data. And then most often, they also have some sort of a server component on premises. So that way, all of these devices can report back and be managed centrally. In the case of a mass update of all of the devices that are out there in the field with a new master drug list or other clinical type settings. So with this particular device, we took a look at the different interfaces that were available to us. So there was 802.11 BGA using standard frequency ranges. So that equipment to assess the security of that part of it was readily available. It had some proprietary power connectors on it. Generally, in order to charge a battery-powered device, you might need voltage in. You might also need some sort of data for smart charging capabilities or some kind of data transfer regarding how much power is left. So we did take a look at that, but didn't find anything particularly interesting there. It also had an IRDA port, normal LCD display, keypad, and what we found was that there was a maintenance mode accessible through the keypad UI with a guessable password. So that provided us with some read-only access to the device. The actual interface in that maintenance mode did have an option to upgrade and downgrade the software. We looked high and low to see if we could find copies of the software and see if we could extract anything from the binary. Luckily, access to that data is pretty well controlled. We weren't able to find anything on that, so we could tamper directly with the device. So the next path that we took was taking a look at the different network interfaces. So since the interface was only readable on the UI, we took a look at a feature of the device which allowed us to change the network settings via the IRDA port. So I had taken a couple different ideas under consideration. First was, all right, well, we could go out and buy an IRDA interface over USB. It seems like the reasonable course of action. But that was going to take a little while to get to us because it's not really a common component anymore. That was out. I had some some IR LEDs and IR sensors in my parts bin, so I considered, all right, do I try and cobble something together with an Arduino and a Raspberry Pi? And I thought to myself, well, that's going to take just as long and probably be 4 times as frustrating. So all of a sudden I had an aha moment. This device was engineered quite a while ago, so I looked at other technology that was available quite a while ago. And ultimately what I settled on was handspring visor. Cost me about $10 at a local pawn shop. So I am one of those people that will hoard electronics from days of yore and say, I'll use that later. And much to my wife's dismay, this did actually prove that point for me in this case. So once we were able to change the wireless settings, we now had the device on our network. So what I'd like to note here is that the overall design of the pump handled wireless communication fairly well. We tried to perform an evil twin attack against the pump. It was completely unsuccessful because it appeared to be checking the server-side certificate on the WPA enterprise network just the way it should have been. Likewise, we tried setting up a rogue access point that didn't have any encryption. It didn't fall for that either. Finally, we couldn't just extract the credentials or the network data using IRDA. So when the update function basically just sent a copy of the configuration template to the Palm visor, and it had some rudimentary authentication mechanisms that we were able to get past because we had physical access to the device. So after we took a look at the template, we found that it didn't share any pre-shared keys in that template. It didn't share any usernames or passwords. So somebody had clearly thought of the security basics here. They just maybe didn't go quite far enough in the engineering of this device. So what we did was we substituted our own information, just hooked it up to our own wireless network. In a clinical setting, this would be raising all kinds of red flags. The device wouldn't be reporting back. So this is more emblematic of what happens with IoT devices that are maybe accessible. Controlling where those IoT devices are can be key because what if one of them gets compromised? Are you able to recover your security if there are key secrets or key trusts that are placed in that device? So that's really what this illustrates here, more than any kind of a James Bond-like or Mission Impossible-like scenario with this particular pump. So once we had the device on our network, we were able to learn a little bit more about the protocols that it used. Notably, we see Telnet FTP, which obviously are plain text protocols. Anything having to do with medical data, medical devices, plain text should be in big red letters a bad thing in any sort of design documentation, whether it's for management or whether it's actually transferring patient data. Obviously with Telnet and FTP, it also sends authentication credentials in the clear. So again, if this were a real world scenario, if for example we were able to get access to the wireless network that these devices were on by some other means, say via VLAN hopping or through compromising another network node, there's a pretty good potential we'd be able to man in the middle, sniff this traffic, and get those credentials. As it is, we just had the device in our lab, so we didn't have any valid clients reaching out with valid credentials, so we had to brute force. In the time that we had, we weren't able to brute force either Telnet, FTP, or SSH. Maybe we just need better word lists. So, in addition to taking a look at the pump from a server side, we also took a look at its natural interactions with the network, and we saw that it was attempting to resolve a certain host name. So, being that we controlled the network, say, okay, we're that host name. What we found when we set up a netcat listener based on that traffic was that it was using a plain text protocol that looks like some ugly XML, followed by a short trailer. It contained a lot of descriptive information about the pump, but not really anything that we would see as sensitive medical data. We tried to respond back with the same sorts of data, and we were getting we were having some varied results there. Mostly we were just getting back what looked to be some kind of a formatted error message. That's until we took a look at the trailer. The trailer that they have at the end of that data turned out to be a simple X-modem checksum. So clearly they were concerned about the integrity of the data in transit, not so much the confidentiality. And the integrity check is good, but it needs to go a little bit further. Given that it was just an X-modem checksum, we could now craft packets that looked as though they were valid, and integrity checked packets from the perspective of the pump. What would be better in this sort of a situation would be something more like a signature as opposed to just a simple checksum. Now, once we were able to send some properly checked traffic back to the pump, it started giving us a lot more information. There were actually two different services. There was one outbound from the pump, and then there was another service going back from the simulated pump server back to the pump itself. And then that service used the same basic data format with a couple of differences. Once we had learned a little bit more about how that communication occurred, we were able to create a custom Python library to interact with the pump in both directions, and we did some fuzzing. There was a message type field in some of that data that we were able to enumerate. We went from 0 all the way up to 254. Most of the message types didn't do anything, but a quick summary of what we learned is here. Type 2 appears to confirm that, yes, I am trying to associate to this pump server. And then type 8 is also a related message, and that's when the pump seems to really say, okay, yes, I'm part of this network. I'm going to start giving you more information now. Type 7 and 31, we're not really sure what they do. They caused maybe a 7 or 8 second delay before responding back with sort of a generic message to us. Same thing with message types 208 and 238. Message type 20 turned out to be a little bit more interesting. That when we sent message type 20, the pump responded back with information about its own wireless card as well as the wireless environment around it. So neighboring BSS IDs, MAC addresses, and signal strengths. So somebody who is able to access this pump and send it a message type 20 might be able to find out where this pump is physically located through similar open source reconnaissance methods. So here's some of the types of data that we were able to get out of the pump once we successfully associated it to our Python library. As you can see up there, it has the pump status, whether it's on AC power or a battery. It also has the drug and the dosage. It even has information about the caregiver that is either programming or administering the pump and its medicine. So clearly there's some protected data there that's potentially at risk if there were an attacker that were able to get a position on this network. Now, I mentioned the master drug list before. That is something that would be pushed down from the pump server to the pump itself. We had some indications that with some of the communication we were able to fuzz. We're highly confident that we would have been able to update the master drug list. We didn't have that pump server software in our lab to view this traffic, and so we could modify it and work off of it. So again, that's kind of a limitation of this particular lab setup. But to be sure, I think that with the other architectural decisions and design features of this pump, I'm fairly confident we could have updated that master drug list. And again, that would have some definitely patient safety, patient care impacts.
Yeah, like one of the things you can do when you can overwrite master drug list is that one of the safety features of infusion pump is that doctors can set a limit to the higher dosage. So for example, they can set a limit to morphine to be 100 milligrams, and once that is set, even if patient wanted to inject more morphine, they can't. But if you can override the master drug list, you can actually cause harm to the patient. All right, so the second device that we looked at was a digital pen. So the pen is used by doctors and medical practitioners to electronically write prescriptions on a special paper, and then that gets electronically transferred to the pharmacy. So the benefit is that you save time. So by the time you reach pharmacy, your medication is already ready for pickup. It didn't look like much of a device, to be honest. Like when you started looking at it first, we thought, oh, the most we can get out of it is maybe like a few prescriptions, and that's pretty much it. Clearly not the case. These devices are manufactured by many manufacturers. We only looked at one device from one manufacturer, and this is definitely not that device for sure. In terms of workflow, the device itself sits on the private hospital network, connects either Ethernet or Wi-Fi, and then the prescription is sent to a cloud server. And on the server side, there's a web portal, so the patients and doctors and admins can log in and see the prescription, an app server, and a database. We initially noticed that it comes with a Windows 10 operating system, so we thought, okay, at least it's not XP. It came with two different accounts. One was a nurse/physician account, so which is typically the account your medical practitioner would use to write the prescription, and then the other one was administrator, which is typically used by device manufacturers to update, troubleshoot the device. I think I was the only other person who used that account. Then there was USB. It had wireless and Ethernet capabilities, HDMI, VGA, standard display port. It came with a fully updated Windows Defender. There was also a docking station, so you can dock the pen on to charge the pen. And software layer, which basically comprised of two applications by the manufacturer. All right, so because it had HDMI, we could connect a monitor to it. Because it had USB, we could connect keyboard and mouse to it. And so we noticed that when you boot up the pen, it automatically logs into the nurse account, which is a lockdown mode, but it was still something. So you had access to Windows 10 operating system in a very lockdown mode. Then there were like a couple of applications that were provided by the manufacturers, and then there were a couple of services that were running by the manufacturer. This pen, so like when doctors use the pen, if it's connected to the internet at that point of time, it will transmit all the data in real time to the pharmacist. If not that, the pen used to store data in an encrypted manner on the disk, and then transmit it over when it connects back to the internet. The data transmission itself happened using SSL, so AES 256, and we looked into it, but there wasn't much in there. There was also a remote access component, which involved using TeamViewer to remote in, again used by manufacturer, which I think could also be a very interesting factor to look at. So like from a pen tester's perspective, we already had access to the operating system, but it was low privilege and locked down. So initial thought was to just update access to local administrators. So basically I could change the screensaver because I didn't like that one. We started looking at different services, and because it was a lockdown mode, we couldn't restart, stop services. We tried some of the exploits that are out there against Windows 10 that also did not work. But then we found this service, which is actually by the manufacturer. Although we couldn't stop the service, we could replace the binary of the service on the disk. Nothing really rocket science here. So we created a payload which would create a local admin user, replaced it with the original binary for that particular application, Since we couldn't restart the service, we just rebooted the pen. So as it came back up, it created a local admin account on the system. So at this point of time, I could indeed change the wallpaper. We also installed some other tools like Wireshark and then also Windows System Internal Utilities. So we started looking at Wireshark, and there wasn't much in there because the traffic was mostly encrypted. I'm not that technical, all that stuff. But after that, we fired up Procmon specifically to look at what are the different events that happen, what are rewrite operations, registry operations, and so on. And if you've ever used Procmon, you'd see that it captures tons of events. And surely, like, you can set a filter to capture from single application, but still ends up a lot of events there. So cycled through them for a long time. And then we realized that the application reads a file with extension .enc. So we figured it will be an encrypted file. We located the file on the file system, opened it in Notepad, and it was all garbage. So yeah, definitely encrypted. Remember I mentioned I am a wannabe reverse engineer, so I put in Ollie debugger in there. Just wanted to reverse engineer the application, so started doing some dynamic and static binary reverse engineering on it. And so, like, after several hours, figured out that the portion on the left side is actually the logic that would decrypt that file. So what application basically was doing was it was reading this file in memory, decrypting it, and then reading some of the parameters from it. So it took another little while to reverse engineer the logic for decryption, and what we ended up doing was just writing a Python script that would locate the file on disk, decrypt it, copy the contents, and paste it on another file. We didn't really have to do it because if you look at the bottom area there, that's already decrypted data. So like when it decrypts it, it will show up there. But just wanted to be a bit more fancy than that, I guess. So we opened the file. If you can see, it has a database string in there. So for MySQL database, so it's got host name, IP address. It's called database name as well. Username, you will see it's root, which is the highest privileged user. There's also plain text password. So we're like, okay, it's there. It has to be written in data. It's there. They're not probably using it. But then we had to do an nmap scan, and there it was. The database itself was exposed over the internet. And like even at this point of time, we are thinking this is like one of those OSCP CTF style things where they want you to think that that's a vulnerability, but it's not really there. But we connected to the database, and there it was. So at this point of time, because we were connected to the backend database and not just through the portal, we could access the patient health record from all the institutions where these pens were installed, and not just our test pen. So essentially millions of records were in there. So if you can see, like I've redacted most of the data because it's real world patient data, but there's patient code in there, patient first name, last name, date of birth, gender of the patient. And then we found tons of data. Like this is another table where you can see the username, email ID, the passwords were in plain text, and then there's something called a role code, and which basically says if this account belongs to an administrator, a manufacturer, a patient. So we pulled out some of the credentials in there, logged onto the portal itself. Here again, you can see the resident name, the unit, home address, room number, HCN is healthcare number, I suppose. And then finally, we were also able to pull out prescriptions that were written by the doctors for different patients. So like tons of them, there's no point collecting all that information. Yeah, so we thought that was pretty cool, but not the prescription part. So these are some of the vulnerabilities that we found in these two devices. It's hard to get your hands on medical devices, so we work on them as in when we get the chance. In terms of closing remarks, I said, like, as I mentioned before, going to be very, very generic. I think Nick did mention some of the good points during his coverage. But I know there's a lot of rush in bringing all these medical devices, not just medical devices, or the IoT devices out to the market, but there isn't any security built into them. They're just trying to bolt on the security as someone finds issues, and it's more like security by obscurity. because not a lot of people are looking at these devices, so they get by in the market. Again, there's going to be tons of medical devices on the network, so from medical institutions' perspective, they have to make sure that they come up with a model to trust the devices and also blacklist the untrusted devices. Nick mentioned that FDA is they've started to pay a lot of attention to medical devices, but we still need to go beyond regulations on that. So I don't know, for whatever reason, as per FDA regulation, once a device is tested and deployed at a health institution, you're not supposed to change anything on those devices because of how they might react to those settings. So, which basically leaves these devices strictly at the mercy of the manufacturer. So the IT technicians at the hospital don't have any insight into the device. So it's kind of a black box for them. We can learn from past mistakes. I think any of the issues that we talked about today aren't exactly 0 days. They have already happened with your web applications, your other hardware, mobile applications and all. So we're not learning anything new here. We just have to be, just learn from the past mistake and use those while building the new devices. And that's it. Thank you.
Thank you, sir.
Good talk.